Okay, so hello everyone, and this is the second installment of my lecture series for differential equations. And on my previous videos, we have formally defined what a differential equation is and how actually it look like. And we also characterize differential equation, whether it is ordinary differential equation or partial differential equation. We also characterize DE in terms of its degree and order and whether it is linear or not linear. So on this video, I'm gonna show you how to verify whether a given solution, whether a given equation is a solution to a given differential equation. And let me just tell you that the solution of a differential equation is an equation or a set of equations. And for this purpose, you shall review your concept of derivatives, because we will do a lot of differentiating for solving differential equations. So let's take a look on this example. Let us verify whether y of x equals e to the negative 2x is a solution to a given differential equation y double prime plus 3y prime equals negative 2y. And then to do this, we shall take a look on our given dE. It contains y prime and y double prime. And this tells us that we shall differentiate y of x twice. We shall get the first derivative and the second derivative. So we shall recall how to differentiate an e function. We shall differentiate e raised to negative 2x. And that will become e to the u, yeah, you can remember that, times the derivative of your u, which is negative 2x. So this led us to negative 2. That's the derivative of negative 2x. You can just write it in front. Then you just copy e to the negative 2x. And we got this. Differentiating it again. So we shall have negative 2 e to the negative 2x times derivative of negative 2x. That's another negative 2. And then you just multiply this negative 2 and negative 2. That will give you positive 4 e to the negative 2x. And then we can now replace y prime by negative 2 e to the negative 2x and y double prime by 4 e to the negative 2x to arrive at this equation. And also y to be replaced by e to the negative 2x. And then again, we shall have this equation, or e to the negative 2x, that is our y double prime, plus 3y prime, which is negative 2 e to the negative 2x, equals negative 2 times y, which is e to the negative 2x. And then simplifying, we shall have 4 e to the negative 2x, then 3 times negative 2 is negative 6 e to the negative 2x, which is in fact equal to negative 2 e to the negative 2x. Then combining these two expression, this is 4, this is negative 6. They are both preceded by e to the negative 2x. So that's negative 2 e to the negative 2x is in fact equal to the expression on the right side. Okay, so since the expression on the left is equal to the expression on the right, then we verified that this is a solution to this differential equation. Okay, let me just show you on my presentation. Yeah, that's it. Okay, and then another one. Verify that y of x equals 3 e to the negative 2x plus 4 e to the x is a solution to y triple prime minus 3y prime plus 2y equals 0. And we have here y prime and y triple prime. So we shall differentiate y of x thrice. Okay, then the first derivative, y prime, equals, so that's 3 e to the negative 2x. So derivative of negative 2x is negative 2. Multiply it to 3. So that's negative 6 e to the negative 2x. Plus, you just copy 4. And you know that the derivative of e to the x is still itself, e to the x. Then y double prime equals, you copy e to the negative 2x. Differentiate negative 2x. That's negative 2. Multiply to negative 6, that will give you positive 12. Then you copy 4, differentiate again e to the x, which is still itself. Then for the third time, y triple prime So you have copy e to the negative 2x, differentiate negative 2x, that's negative 2 again, times 12, that will lead you to negative 24. Then again, copy 4, then you copy e to the x since its derivative is it's still itself. So you got these derivatives. Okay, and then the next thing we need to do now is to replace y triple prime and y prime and y by the equations we obtained earlier. So you have y triple prime, okay, is equal to 12, oh, that's negative 24 e to the negative 2x plus 4e to the x minus 3 times y prime, where y prime is negative 6, yeah, e to the negative 2x plus 4 e to the x, right? Then plus 2 times y, wherein y is 3 e to the negative 2x plus 4 e to the x, and we shall equate it to 0. Sorry for that one. And then we can now simplify this further. You have negative 24 e to the negative 2x plus 4 e to the x, negative 3 minus times negative 6, so that's positive 18 e to the negative 2x. I am just distributing negative 3 each term inside the parentheses. The negative 3 times 4 is negative 12 e to the x. Then you do the same here. Plus 2 times 3, that is 6 e to the negative 2x. Then 4 times 2, it's 8 e to the x, and then you equate it to 0. So we shall be expecting that the whole bunch of expression on the left side should be equal to 0. Where then we can combine negative 24 e to the negative 2x plus 18 e to the negative 2x is negative 6. Negative 6 e to the negative 2x plus 6 e to the negative 2x, that is 0. Then 4 e to the x minus 12 e to the x, that is negative 8 e to the x plus 8 e to the x. In fact, that is equal to 0. And that is equal to the left side. So that 0 equals 0, and that we now verified, sorry, that y of x equals 3 e to the negative 2x plus 4 e to the x, a solution to this given differential equation. Okay, let me just show it up to you, right? And we can now see that 0 equals 0. Okay, so from these two examples, we can now see that when you are given a solution, then we can easily verify whether it is a solution to a given differential equation by just differentiating and then substituting it to the given dE. Let's try another one. Say this time we shall verify that L and Y equals C sub 1 e to the x plus C sub 2 e to the negative x, where C1 and C2 are constant, is a solution to the differential equation y double prime minus the quantity y prime squared equals y prime L and y. And again, the differential equation includes y double prime and y prime. And then we have here L and y. And you recall that the derivative of an ln function, ln x, is 1 over x dx. Okay? So we shall now have ln y equals c sub 1 e to the x plus c sub 2 e to the negative x. Differentiating this implicitly, so you know that the derivative of ln y is 1 over y. Then by implicit differentiation, since we are differentiating with respect to y, you affix y prime equals, you copy c sub 1, that's constant, differentiate e to the x, then copy c sub 2, that's constant, and then you differentiate e to the negative x is negative e to the negative x. So you shall have 1 over y prime equals c sub 1 e to the x minus c sub 2 e to the negative x. And then, since we have here y double prime, we shall differentiate this again. To differentiate 1 over y prime, we shall use derivative of product. You recall, that's u dv plus v du. Okay? The first times derivative of the second plus the second times derivative of the first. So you have 1 over y times the derivative of y prime, that's y double prime, plus y prime, times derivative of 1 over y is negative 1 over y squared. And since again, we are differentiating with respect to y, you affix y prime equals c sub 1 e to the x, then copy c sub 2, differentiate e to the negative x, that's e to the negative x times negative 1, that's the derivative of negative x, and then this is preceded by minus sign, so we shall affix the plus sign here. Okay, so we shall now have 1 over y double prime, plus y prime times negative 1 over y squared y prime equals c sub 1 e to the x plus c sub 2 e to the negative x. Or this can now be written as y double prime over y, then this is plus, this is minus, so that's minus y prime times y prime, that's y prime square all over y squared equals the right side. And then what are we going to do? To eliminate the denominator y and y prime, we shall multiply everything by y squared. Okay, so you have y double prime over y times y squared is y double prime, and we are getting there because we now have this y double prime. Okay, right? And we're getting close. And then y prime squared over y prime times y squared, sorry. Then you'll have y prime square, okay? You see that? And then equals y squared times c1 e to the x plus c2 e to the negative x. And then the next thing we need to do is to eliminate this part, okay? So we have this, and then you can see from here, right, that c sub 1 e to the x plus c sub 2 e to the negative x is in fact our ln y. So you can replace this by ln of y. And finally, we arrive at our final answer. Yeah, that's y double prime minus the quantity y prime squared equals y squared. And what is this? That's ln y. And we have already verified that this equation is a solution to this differential equation. Okay, so what did you notice on from this three example is that we shall eliminate those constant. Okay, so here we need to eliminate the C1 and C2 so that we can verify that this is a solution to this differential equation. Okay, and then again from our previous examples, we see that if we were given a solution, okay, to a given differential equation, then we can find this differential equation by applying a method called elimination of arbitrary constants. Okay, so which means if you wish to find the differential equation from a given solution, then we can use one of this technique called elimination of arbitrary constants. Okay, and then let us try to apply this method. Say we wish to find the differential equation, okay, related to or y equals c sub 1 e to the negative 2x plus c sub 2 e to the 3x. Remember that this equation, y equals c sub 1 e to the negative 2x plus c sub 2 e to the 3x is a solution to the desired differential equation that we are going to look for. Okay, now, so we can see that there are two constants here, C1 and C2. And remember that the number of arbitrary constants, no? So we say that it's arbitrary because we can replace those constants by any number. So that's arbitrary constants, okay? So the number of arbitrary constants present on the equation will determine the number of times you are going to differentiate the function or the equation. So here, there are two constants here, C1 and C2. So we shall differentiate it twice. Okay, so this is the first derivative. And you just copy y prime equals, you just copy c sub 1, and then copy e to the negative 2x, and then differentiate negative 2x. And that's negative 2. Plus c sub 2, you copy c sub 2, you copy e to the 3x, then you differentiate 3x, that is equal to 3. And you got this first derivative. Differentiating it again, since there are two constants, so you have y double prime equals negative 2 c1, then e to the negative 2x times differentiate negative 2x again, plus 3c2, I just write this in front, copy e to the 3x, then differentiate 3x, that is 3. And you got this second derivative. 4c1 e to the negative 2x, that's negative 2 times negative 2, that's why it's 4. And then 3 times 3, we have 9, c2 e to the 3x. Okay? Next. So, to eliminate c1 and c2, that is our goal. Okay, so we mark this equation 1, equation 2, and equation 3. So we shall apply the usual method. Yeah. If you can still remember how to solve systems of linear equation by elimination, we shall apply the same method here. Okay, so our goal is to eliminate C1 and C2. So I can now use equation 1 and 2 to eliminate C1. So we shall eliminate first C1, but you can also do it in C2. You can eliminate C2, but allow me to eliminate C1 for this particular example. So to do that, you know that's on the first equation, I'll be using equation 1 and equation 2. And when you see C1 here, the coefficient is 1, and here the coefficient is negative 2. And for you to eliminate this, okay, their coefficients should be equal, whether it is of similar sign or different sign. If they have similar sign, you subtract. If they have different sign, you add. So this time, I can multiply positive 2 to equation 1, and then I will add equation 2. Okay? So you have 2 times y is 2y, right? Equals 2c1 e to the negative 2x plus multiply 2 again, 2c2 e to the 3x. And you have this. Okay, so you multiply 2 to equation 1, that's 2y, equals 2c1 e to the negative 2x plus 2c2 e to the 3x. And then we shall add equation 2. This is your equation 2. And you can now see that when this is added, this will become 0. Okay, so we shall add. So 2y plus y prime is 2y plus y prime equals, this becomes 0, then 2c2 e to the 3x plus 3c2 e to the 3x, that will lead you to 5c2 e to the 3x. And you have this. And we shall mark this equation 4. Okay? Doing the same for equation 2 and 3, eliminating the same variable, c1. So this is negative 2, this is 4. We can only eliminate c1 if we multiply 2 to equation 2, so that they will have the same coefficient, and then we shall add equation 3. So multiply 2 to equation 2 and add equation 3. So you'll have 2y prime equals negative 4c1 e to the negative 2x plus 6. Yeah, that's 2 times 3. c2 e to the 3x. Then you add equation 3. Y double prime equals 4c1 e to the negative 2x plus 9c2 e to the 3x. And the process is addition. So you shall have 2y prime plus y double prime equals, this becomes 0. Then 6 plus 9, 15. c2 e to the 3x. And then this shall be marked equation 5. Now, when you see equation 4 and 5, there's only one constant, C2. So we can use equation 4 and 5 by elimination again. And that can be done if we multiply 3 to equation 4. And then, since they have the same sign, yeah, both positive, then we can subtract. So multiply 3 to equation 4 and subtract equation 5. So you have 3 times 2y is 6y. Plus 3 times y prime is 3y prime equals 15 c2 e to the 3x. So you have this. And then you subtract equation 5. Okay? So you have 6y 6y plus 3y prime minus 2y prime minus y double prime equals 15c2 to the 3x minus this will become 0. And we now arrive at the differential equation that we are looking for. The only thing we need to do is to combine things that need to be combined. So you have 6y, 3y prime minus 2y prime is y prime, yeah, minus y double prime equals 0. And then you got this. Or you can just make y double prime the leading term. You can just multiply this by -1, and that will lead you to y double prime minus y prime minus 6y equals 0. And we have this differential equation. Y double prime minus y prime minus 6y equals 0. Okay, another example. This time, we have x squared y equals 1 plus cx. And again, the goal is to find the differential equation with x squared y equals 1 plus cx, one of the solutions. So we have only one arbitrary constant, and we have only c. So how many times are we going to differentiate? Again, the number of constant will determine the number of times we are going to differentiate the function. So since there's only one arbitrary constant, then we just shall differentiate it once. Okay? We just copy the given, and then we shall differentiate this by derivative of product. So you have x squared times derivative of y is y prime, right? Then plus y times derivative of x squared, 2x, by applying derivative of product again. You know that the derivative of 1 is 0, plus derivative of cx is c. So we have this equation. And then we just simplify this part, leading us with x squared y prime plus 2xy equals c. And after the first derivative, c is still there. Okay? So what are we going to do? You take this equation and then you replace c by this. So you have x squared y equals 1 plus c, where c is x squared y prime plus 2xy and then times x. So we have this equation. So we can now distribute x, each term inside. Come on. So you have x squared y equals 1 plus x times x squared is x cubed y prime plus x times xy will become 2x squared y. And then you have this. So we can write this of the form, yeah, x squared y plus x cubed y prime plus 1. And how do you do that? You just throw this on the other side, and then you combine with 2x squared y. So that led you to x squared y plus x cubed y prime plus 1 equals 0. Okay, another one. Let me see. Or, yeah, you can replace y prime by dy dx if you want to use the Leibniz notation. So that's x squared y plus x cubed dy dx plus 1 equals 0. Or, okay, you can combine this x squared y and 1, x squared y plus 1, okay, plus x cubed dy dx equals 0. Or you just multiply this by dx, so you can write this of the form x squared y plus 1 dx plus x cubed dy equals 0. All right. So these two differential equations mean the same thing. Example number 3. X equals a sine omega t plus b, and we have to take note that omega is a parameter. If you see this note that a variable or a constant is a parameter, then it should not be eliminated. Okay, so here there are only two constants, a and b. Omega, okay, and t are parameter. So and they need not to be eliminated. So we have to eliminate a and b, since these are our arbitrary constants. And then to do that, we shall differentiate this twice. Okay, so you have dx dt equals, we are differentiating with respect to t. You copy a, that's constant, and you know that the derivative of sine is cosine. You copy omega t plus b, and then you differentiate this and that is equal to omega. Derivative of omega t plus b is equal to omega, and then the derivative of b with respect to t is 0. And then so we can write it of the form a omega cosine omega t plus b. Differentiating this again, you have the second derivative of x with respect to t. You copy a omega, you differentiate cosine, that's negative sine. You copy omega t plus b, and then you differentiate omega t plus b with respect to t, we'll have another omega, and that will lead us to negative a omega square sine omega t plus b. Okay? And then, how do we eliminate b and a? We can see here that the second derivative of x with respect to t is equal to, let me see, negative omega squared. Then I will combine this a sine omega t plus b, right? Because I can replace this by, from our given, by x. So this is our x. And then we shall have, right, the second derivative of x with respect to t equals negative x omega square. Okay? One more? Yeah, and that is our final answer. The second derivative of x with respect to t plus x omega square equals 0. Another one. Let me see. Yeah. Y equals x plus c sub 1 e to the x plus c sub 2 e to the negative x. We're looking for a differential equation in which this equation is a solution, a member of the family of solution. So again, we have two arbitrary constants, C1 and C2, and we shall differentiate it twice. We shall write the given first, and okay, we shall differentiate this. So you have y prime equals derivative of x is 1 plus copy C1, differentiate e to the x, that's simply e to the x, and then copy C2, copy e to the negative x, derivative of negative x is negative 1. So we shall have this. Differentiating it again, you have y double prime. You know that the derivative of 1 is 0. You copy C1 again, differentiate e to the x, so that's e to the x. Then copy C2, copy e to the negative x, differentiate negative x, that's negative 1. Multiply it here to another negative 1 here, so that will become positive. Okay? So you have y double prime equals c sub 1 e to the x plus c sub 2 e to the negative x. And then doing the same, we're going to eliminate c1 and c2. And you can now see that this is c1 e to the x plus c2 e to the negative x. And then from here, right, we can now say that y minus x equals c sub 1 e to the x plus c sub 2 e to the negative x. Right. Okay, so we can now replace this by y minus x, and eventually we can now have, right, y double prime equals y minus x, and that's the differential equation in which this is one of the solutions. That's y double prime minus y plus x equals 0. Okay, so we did not apply, the usual elimination of the usual process of elimination, because we just simply use substitution to eliminate the arbitrary constants. Okay, another example, let me see. All right, we have y equals c sub 1x squared plus c sub 2 e to the 2x, and then we have two arbitrary constants again, c1, c2. And then we shall eliminate the C1, C2 to arrive at a differential equation. So we shall write the given first, and we can now differentiate. Okay, so we have y prime equals C1, derivative of x squared is 2x, and then copy C2, e to the 2x, derivative of 2x is 2. Okay, and then you affix the plus sign. And then you have this. That is mark our equation 2. Then differentiating it again by following the same technique. All right. So you have equation 1, 2, and 3. And then by elimination, we can eliminate C1 or you can eliminate C2. And that can be done if you multiply 2 to equation 1. All right. And then, or, let me see. All right. Yeah, we multiply 2 to equation 1. So we have this. And then subtract equation 2. So we need to subtract since both c1x squared and 2c1x are preceded by plus sign. So we need to subtract. They have similar sign. And then you have 2y. So 2 times y is 2y. 2 times c1x squared is 2c1x squared plus 2c2 e to the 2x. And then we subtract equation 2. So you shall have 2y minus y prime, right? Equals, this will become 0. And then we shall, oh, no, this is not 0. Sorry. This is not 0 because this is x squared and this is x. So you have 2c1 x squared minus 2c1 x. And then this will become 0. That's it. Yeah. Okay. So this will be marked equation 4. Right. That is our equation 4. And then doing the same for equation 2 and 3. So what did we eliminate here? We eliminate C2. So we eliminate C2. So we shall do the same here. To eliminate C2, remember this is 4, this is 2, so we shall multiply 2 here. So we shall multiply 2 to equation 2 and they have similar sign. Subtract equation 3. Yeah, right. Yeah. So multiplying 2, so you have 2y prime equals 2 times 2c1x is 4c1x plus 2 times 2c2 e to the 2x is 4c2 e to the 2x. And we have this. And then we shall copy equation 3 and then we shall subtract. Subtracting the two equations, so you have 2y prime minus y double prime, then equals 4c1x minus 2c1, and then this will now become 0. Okay, so we shall now have this. All right, so what did you notice? From equation 4 and equation 5 still have c1. So to eliminate that, okay, this is another way to eliminate c1. We can use, simultaneous equation. So I can factor out c1 here. So that led me to this equation. 2y minus y prime equals, you factor out c1 times the quantity 2x squared minus 2x. Or 2y minus y prime over 2x squared minus 2x is c1. And then you do the same here. So this is 2y prime minus y double prime over 4x minus 2. Sorry. Okay. Equals c1. And you have this. That's our c1. And then we shall equate this to c1. And then you have this equal to 2y prime minus y double prime over 4x minus 2 is equal to 2y minus y prime all over 2x squared minus 2x. And then, actually, we can drop 2 off here. So you can drop 2 here. You can also drop 2 here. And then we shall have, by cross multiplication, you can drop 2 here. So this will become 2x minus 1, right? And then this will become x squared minus x. Then you cross multiply. So you have 2y prime minus y double prime times x squared minus x equals then 2y minus y prime times 2x minus 1. Okay? And then we can now have, we shall distribute this 2y prime, each term here. So we have 2y prime times x squared minus x, yeah, minus y double prime times x squared minus x equals, you do the same, 2y times 2x minus 1 minus y prime times 2x minus 1. And we have this equation. Okay? And then what I did here is I just, transpose this on the other side. That's why this is -2 and this one is plus y prime. Okay, again, this is 2y times 2x minus 1 minus y prime times 2x minus 1. And then these two expression are transposed on the other side. That's why this is -2y 2x minus 1 and positive y prime 2x minus 1. Yeah. And then we can now combine this 2 having y prime in it here and here. So you factor out y prime, okay? Then 2 times x squared minus x, and then here, then plus 2x minus 1. And then you copy everything here. So minus y double prime times x squared minus x minus 2y times 2x minus 1 equals 0. And then we can simplify this part. That will lead you to 2x squared minus x plus 2x, or sorry, this is minus 2x. We have 2 here. 2 times x squared is 2x squared. 2 times negative x is negative 2x. Plus 2x minus 1. And then this will become 0. The only thing left is 2x squared minus 1. So we have this. Okay? Y prime times 2x squared minus 1 minus y double prime times x squared minus x minus 2y times 2x minus 1 equals 0. And this is the differential equation that we are looking for. Okay? Do we have still another example? Or you can, yeah, another way to do this is to make y double prime our leading term. So that's negative y double prime x squared minus x. But you can stop here. I think this is still accepted to be the desired differential equation. So that's negative y double prime times x squared minus x plus y prime times 2x squared minus 1 minus 2y times 2x minus 1 equals 0. And then you just multiply this by -1 so that the leading term shall be positive. Yeah. And these two differential equations are equal. I think we still have one final example. Say y equals c1 cosine x plus c2 sine x. So again, we have two constants, c1, c2, and we shall eliminate that c1, c2. Okay, so we shall write our given first. Y equals c1 cosine x, c2 sine x. Remember that the derivative of cosine is negative sine of x, and then that the derivative of sine of x is positive cosine of x. Okay, so differentiating, you have y prime equals, copy c1, derivative of cosine x is negative sine of x, copy c2, derivative of sine x is cosine of x. And then we shall have this. Differentiating it again, we have this equation, y double prime equals negative c1 cosine x minus c2 sine x. When I factor out -1 here, so c1 cosine of x plus c2 sine of x. And then you can see that this is in fact our y. So therefore, y double prime equals negative. What is this? Our y. So we have y double prime plus y equals 0 is the desired differential equation with c1 cosine x and c2 sine x a solution. Yep. And finally, we have y double prime equals negative y. And yeah, and we're done. So you just keep on tuning in for more videos in solving differential equation.